real time. And I'm not going to just do some talking, I'm also going to demonstrate in real time what we can do. So just to give you a brief introduction into who will be talking with me, or who has worked with me on this topic. We have Professor Ross Anderson sitting right here. We have Paul Taylor, who unfortunately couldn't be here today. Ronald Poppe, who will be taking care of the technological bits. And we have Ramsey, who will be giving a live demonstration himself. Mark Frank already mentioned it a bit this morning. Why is nonverbal behavior interesting? Well, whenever there's an incongruent message, which might happen when you are lying, actually the nonverbal message comes across better than the verbal message does. So I can say something really, really friendly, like, I love your tie. But if I say it in a very sort of aggressive way, or my facial expressions don't match what I'm saying, then it actually won't sound that nice. So it doesn't necessarily mean what I say, but how I say it. However, as any one of you knows, all the meta-analysis on nonverbal cues to deception have not been that great. There's no nose of Pinocchio. There's a lot of contradicting findings. Sometimes there's more hand movement, sometimes there's less hand movement. And the types of cues that do go in the same direction often have very small effect sizes, so they might be hard to spot. So this makes me wonder, is this time to give up? So maybe there are no nonverbal cues. Some researchers thought that that's the way to go, but I wasn't ready to give up yet. So instead I thought maybe we need to measure it differently. Because if there was one thing that I noticed when I was going through all the different studies that have been done on nonverbal cues, I realized that we all do that in a very similar way, at least up till a few years ago, which is you get a participant and you instruct them to do something, for example, lying. This behavior is then going to be video recorded. And then, I don't know who of you have ever tried, but then you sort of sit behind a computer and you slave away for several months to make sure that you code every little or annotate every little behavior that people did. So that looks a bit like this. This is a screen where you have a therapist and a client, and you can see her from two sides. You can slide through time over here, and these are the different types of behaviors for both people. And you sort of annotate whatever behavior is happening for every moment in time. And what that basically does is it reduces movement to a binary decision. Forgive me, I'm in computer science now, I can say this. So what you actually do is you want to see if someone moved his hand or whatever body part you're coding at that point at this moment in time, yes or no. That means that you're not taking into account the magnitude of a movement. So in practice, it matters quite a lot if I make a movement like this to accompany my speech, or if I'm gesturing like that, like an Italian. But that's like, it's a code yes or no. Did someone move his hand, yes or no? So it doesn't take any of that into account. Also, as I'm talking at the moment, I constantly move a bit. I swift from one side to the other, I move my hands, move my shoulders, and because it's sort of a trade-off whenever you code behavior, it's a trade-off between how many movements you can code and how much months you have to spend doing that. Which means that you usually don't code a lot of different behaviors, and you usually don't take the small movements into account either. The direction of movement might be very useful, especially if you're talking about your alibi, where you were last night, I was going that direction, is not taken into account either in manual coding, and neither is the velocity of a movement. Is it a very slow movement, or are you moving really rapidly? So when I realized this, I figured that maybe there are not that many nonverbal cues to deceit that are reliable. Might be possible. But maybe we have been overlooking these cues. Maybe we've just not been measuring them right. So then the question basically was, is there an alternative? And that is how I ended up in computer science. When I was doing a psychology PhD, I sort of excitingly went to the University of Twente, which is a technical university in the Netherlands, and I said, I'm interested in measuring nonverbal behavior in an automatic manner. What can we do? And this is what we can do. It's a company that was actually a spin-off from the University of Twente. It's called Xsense, and it's an inertial full-body motion suit. And you can use it to, well, show people how you move. Gordon, do you want to show things? So this is my model for today. This is Gordon. And what you can see here is that there is a 3D representation of Gordon right there. Whatever he does, the skeleton man does as well. So how people normally know this kind of behavior is because it's been used in Hollywood and in the gaming industry for special effects in movies and animations. However, we're not putting any Gollum on top of Gordon because we think he already looks quite well. We're just interested in how he moves. So nowadays, it's not only being used for animations, but also for research purposes, because with this technology, because you have several sensors across the body, it's a very accurate way to track movement and body motion. So this is, like you can see Gordon, whenever you would have an interview, this interviewee was not very cooperative, I would say. And this is how the visuals look like, and this is how the raw data looks like. So this is what we actually analyze. So just to give a very brief overview of what we do, we have, thank you very much, Gordon. A bit of an applause, please. Thank you. So what we do is we take this 3D image that you just saw of time frame 1 here, and then we take the next time frame, put it on top of each other, and then we measure the distance between the different joints that we were measuring. And that way you get a sort of overall movement measure, and you can calculate one per second, for example. So how many centimeters per second do people move? You can do this for the entire body, or just for the things you're interested in, like hands, arms, head, trunk, whatever pleases you. So we did a study on this, and we published it at Higgs about 8 months ago. So some of you might have already heard about it, so I'm not going to go into too much detail. But this is sort of how it looks like. We had 2 participants, an interviewer and an interviewee, and they did an interview about 2 different tasks. So what we did is we had 90 participants in total, 90 interviews in total, 2 participants per interview. So we had a participant interviewer and a participant suspect. And they were from 3 different cultural groups. We had British people, South Asian people, and mixed interviews with a British interviewer and a South Asian suspect. People or told the truth or a lie, and we also manipulated interviewing technique, and we did that within subjects. So we did the normal interviewing or reverse order questioning. So the main question, of course, now is, did lying affect people's movements, yes or no? Yes. So to start off, in blue you can see the truth, and in the sort of whitish you can see the lies. So when people were talking in chronological order, liars moved about 1/3 more than truth tellers did. And whenever we interviewed them in reverse order, the difference actually became almost twice as much. There was a main effect for veracity. That means that overall liars move more than truth tellers, and there was an interaction between veracity and interviewing technique. Culture did not influence body movement at all, in the sense that not when it came to lying, but also not for their overall body movements. So this is interesting, very interesting from a theoretical perspective, but in case you're interested in if the individual in front of you was lying or not, we also did an analysis for that. We all know by now, meta-analysis, of course, with interviewing techniques, you can up that number, you can do different things, but in general, humans are not that good at detecting deceit, 54%. In our study, the interviewers indeed were about 53% right, so that's very similar. Just to give it a bit of a comparison to another type of technology that you can use to detect lies, there's a few different numbers out there dependent on being commercial or scientific research, but one of the numbers that came from the recent book on this topic was between sort of 61 and 83% accuracy, and we reached an accuracy rate of 82. So at least we're doing quite well. How stable that is, we need to figure that out still. I'll skip through this one for now, because it's almost time to hand over to my colleague, because there are a few issues with this new technology. One of them is that it's a new method, which means it needs to be validated, and preferably by all of you, not by me, because I've sort of done that. We've now collected several data sets, and every data set, movement goes up when people are lying, but the amount that it goes up differs a bit between the studies. And the other problem is that wearing a full bodysuit, Gordon might tell you in the break, may actually alter people's behavior and make it difficult to implement in practice. It's not very ecologically valid if you're wearing a suit like that. So that's where Ramsey comes in. We have now been working on an unobtrusive way of measuring behavior, and we're going to show you what we've done over the past few months.
Sophie. Can everyone hear me okay? I can hear myself very loudly, so I guess you can. So, yes, where I came into the story was the team were interested in moving away from about £30,000 worth of very expensive sensors mounted on a body and moving towards a kind of standoff capability. So could we develop a very cheap sensor set which someone could just walk in front of without having to put anything on, and the lie detection process could work? It would be more covert, be quick, cheaper, easy to get going. So we did a down select on a number of sensors we could use. The Kinect is a fantastic core technology for us to work with. So for those who aren't familiar with it, it's a games console toy. You hook it up to an Xbox, you dance around in front of it, pretend you're playing tennis or whatever. It can sense what you're doing and put you in the game. So it's a depth camera that then overlays a skeleton on people, or what it thinks people in the scene. So we can get the data out of this similar to the data that comes from the sensors mounted on someone when they're wearing the Kinect. When they're wearing the motion capture suit. A problem with the Kinect is that it's a line-of-sight technology. So if you put your hands behind your back, it can't see them anymore. So if I'm waving my hands frantically, the Kinect can't see that. The mocap would still, the motion capture suit would still detect that. So we also implemented a radar as well. So the radar can detect things that the Kinect can't see. And so if someone was perhaps wearing a very large shawl, say, and their hands and their feet and their legs were covered under this large robe, the radar would still have some hope of detecting motion in places that the Kinect can't see and things like that. So in terms of the trade-offs we're looking for, the motion capture suit is very accurate but very expensive. Ideally, we want to be very accurate and very cheap. The two technologies we're working with on their own have a range in their performance, but they're very low cost. And through sensor fusion algorithms and signal processing, we developed a rig which moves towards the ideal zone. And one of the great things about the sensors we're using is the efficiency we automatically get from them. So the motion capture suit is both very expensive, but very inefficient in the time taken to put it on. So how long did we take to rig you up? 10, 15 minutes? You wait till you have to take it off. These things work very, very quickly, as I will demonstrate in a moment. So what you get out of the sensors, the Kinect generates this sort of heat map looking thing of depth. And then the Kinect overlays a skeleton using a whole host of very clever machine learning libraries to basically say, I reckon this funky shape in front of me might be a human. Let's try and fit a skeleton to it. I can fit this skeleton to it best. So let's pass that data out as being the hands, the elbows, the head, and so on. Of course, that suit, an accelerometer and gyro is mounted directly onto the elbow. So it's very high integrity. It's very confident that that's what the elbow is doing. Whereas the Kinect has to sort of infer what's going on. The radar data is a bit of a double-edged sword. This radar will just spray its pulse in every direction. So the demo in a moment, you'll see you guys will be picked up by the radar just as much as me. And in this room, to this radar, this is a hall of mirrors, so that the information is bouncing around all the time. So we have to do some processing to get down to just the radar pulses we're interested in. And a radar pulse generally returns all of this scruff. It's called clutter. Lots of stuff you're not interested in. So actually fuse the data from the Kinect into the radar to help guide the radar to understand where the person is. So the radar hopefully just pays attention to the person it's looking at. And radars can do some really cool stuff. So these radars are very cheap now. This is about £1,000, which might not sound that cheap, but in the context of where radars have come over the last 10 or 20 years, the prices are tumbling. And radars have been used to do things like detect people's pulse rate and breathing rate at standoff. So there's lots of interesting things we can do with radars. One of the challenges we have going forward that we're still working on is getting the Kinect to be able to work just as well as the motion capture suit. So this is someone sat down with their legs crossed according to the motion capture suit. And the mouse pointer has disappeared, which is making life challenging. Here we go. So that's someone sitting down with their legs crossed according to the motion capture suit. You're about to see the Kinect overlaid. And the Kinect is great at people stood up. All of the machine learning stuff they've done that fits skeletons to blobs is great when people are standing up playing tennis. It's not great at dealing with legs when people are sat down. And in this instance, the Kinect thinks that the person's legs are both together, knees together, feet together. So the Kinect has done a bad job of getting their exact pose. And you'll also see there's some jitter on the hands and the feet, because they're the things that the Kinect, so those blue lines are just marking the discrepancies in the joints against the mocap in red, the motion capture suit in red, and the connect in green. So we've still got some of these challenges that we're fixing at the moment to do with getting the connect's estimates of joints as good as the motion capture suite's estimates of joints. But we are getting there. We know how to approach fixing these problems. It's to do with simply the Kinect being a black box that's designed for gaming, and we're trying to make it something else. So live demo time. Are we fired up? Okay, so I will just do this. And could you try flicking to East Bench on there and see if it works? So, so what were you, 10 minutes setup time? There we go. So it's stalled. Is it live on there? Yeah. This could be, I think this is just the frame rate because you're running the motion capture suite on the same laptop. So this normally runs quite a bit faster, but it's trying to cope with the motion capture suite running at the same time. So the top left is my skeleton according to the Kinect. The bottom left is the motion estimate of all of my limbs according to the Kinect. So I do some strong motions and it gets picked up, and that's sort of a metric that can be used for motion. The top right is the radar. The two blue lines are the bit of the radar pulse to be interested in according to the Kinect data. So the stuff between, can you move a mouse or something? Love live demos. Okay, cool. The bit between the blue lines is me, and technically anyone else within 2 meters of the radar. So if you guys could stay still, that would be great. I'll stay perfectly still. You'll see the radar pulse drop away, and then I'll start breathing heavily, and the radar will pick up my heavy breathing. So here we go. See, so that's just detecting the changes in the motion of my neck and my chest. So the radar is incredibly sensitive. And if I was wearing a large shawl, stuff that the Kinect couldn't see, the radar would be able to pick up these motions. Sorry for the very engineering mode MATLAB stuff you're looking at, but you know, this stuff has only been going for a couple of months and is still work in progress. I'll hand back over to Sophie to wrap up.
Thank you very much. Do you have the clicker? Okay, so just to conclude, most research on nonverbal indicators of deceit have mainly relied on manual coding, except for a few groups. Motion capture suites can more objectively measure nonverbal behavior than we could manually. Our results so far keep suggesting that liars move more across all limbs, but that might have to do with context as well. So we would love it if other people start trying this as well, and then we can see how stable it is across labs and across situations. And lastly, what we've been working on so far, unobtrusive measurements, very useful because they can make things more cheaply and therefore more easily available for other people to start trying. If the Kinect starts to work at some point, we will actually have a lie detector in your living room that your kids are playing with. That's a bit scary and something we might want to talk about at lunch. And they're promising so far, but they definitely need some refinement because it isn't as accurate as some of the other ones. Yeah, we'll skip that. Special thanks to our model, Gordon. You're awesome. Thank you.